So now you know what we can see in a 3D graphic extension, but how do we see it? Now on screen you can see a representation of how you actually see in real life and what we're trying to simulate in a graphic extension. So the user will be the little model of a person down in the bottom right corner. The person's eyes will be where that black dot is right in front of him. The 4 black lines here define the user's cone of vision. Now since screens are rectangular, this cone is going to look much more like a pyramid than an actual cone. The plane in front, the one with the grid on it, is what we're going to call the near clipping plane. This means that anything before that plane will not get rendered on screen, and everything after will. This is also a representation of what the screen will be. So the grid you see on the near clipping plane represents basically the pixels on your screen, so every little square will represent 1 pixel. The plane you see in the background, the one that's all white, is going to be the far clipping plane, and that's going to be the farthest we'll possibly be able to see in the 3D graphic extension. Now let's say we want to represent our primitive on screen. Now we said earlier that every model is created by a strip of triangles, but for the sake of simplicity here we're only going to represent 1 triangle. Now as you can see, this triangle is somewhere between the near clipping plane and the far clipping plane. That means the user will be able to see it. But how do we transpose this triangle that's in the middle of nowhere onto the near clipping plane, which represents the screen? We do this with the process we call rasterization. Now remember, we said that every triangle was made of 3 points, and these points were all defined in a 3D space. That means we can find the 3D space in which every vertex of this triangle is, and we also know the black point where the user sees. So that means we have 2 points, and with these 2 points we can make a line. So we're just going to make a line between where the user sees and every vertex of the triangle. Since the near clipping plane is also in a place defined by 3D space, we can find the intersection between the lines and the plane. And this is where the vertices of the triangle will lie on the near clipping plane and also on the screen. So now that our vertices lie on a 2D space, we can forget the 3D aspect of it and just concentrate on the near clipping plane. So here's the near clipping plane, and here's where the 3 vertices intersected with the near clipping plane. Now if we go through every possibility of connecting these dots together, we'll end up with a triangle, since there's only 2 ways to connect one dot to any of the other dots, and there has to be 2 sides that come out of every dot. So we'll obviously always end up with a triangle. Now since we know the positions of every vertex on the screen, we can define for sure where the triangle is not. So we can take the largest y-coordinate and the smallest y-coordinate, as well as the largest and smallest x-coordinate of every vertex in these triangles, and make those the top, bottom, left, and right sides of a box. Now this bounding box, that we'll call it, comes in handy when we have to apply the edge function to every pixel. The edge function is used to determine whether a point is on the right side or the left side of a vector. So as you can see here, the function takes in 3 arguments basically. A first point, a second point, these 2 points will make the vector, the second point being the direction where it points, and a third point, which in our case will be the center of a pixel. Now basically, if the center of the pixel is to the right of the line, it'll have passed the edge function. That means that the edge function will return a value that's greater than 0. If the point is on the line, the edge function is going to return a value that's equal to 0, and if it's to the left of the line, it's going to return a value that's less than 0. Now for every pixel in the bounding box, we're going to apply the edge function 3 times with the 3 vectors that we could see that make up the triangle. If it passes the edge function 3 times, that means it returns a value greater than 0 3 times, the pixel will be colored, and it's going to be colored the same color as the triangle. You can see where the bounding box is helpful here. Instead of having to iterate over every pixel on screen, you can iterate over every pixel in the bounding box, and the result will necessarily be the same. So once that's done, you end up with a triangle that looks like this. Now you might say, well, that looks really blocky, and you'd be right. But on a real screen, that triangle would be really small. But there are still ways to reduce this blockiness, and that's called anti-aliasing. So anti-aliasing is done by splitting up every pixel into subpixels. Now, in our example, we're going to do 4 times anti-aliasing. That means that on every width and every height of pixel, we're going to separate it 4 times, making 16 subpixels. Now, lines don't care what the pixels look like, so we can still apply the edge function to every subpixel. And as you can see on screen, this makes some pixels that are partially filled and partially unfilled. But this is kind of cheating because we can't really represent parts of a pixel on screen. So how do we solve this? We can count the amount of subpixels that are filled versus the ones that are unfilled within a certain larger pixel. So let's say there are 5 subpixels filled out of a larger 16 subpixel sized pixel. That means that that pixel will be 5/16 red. And if we apply that to every pixel in the bounding box, what we get is a triangle that looks like this. It's not perfect, but it's much smoother. And we did 4 times anti-aliasing, but there exists up to 32 times and 64 times, which will make 64 squared subpixels in every pixel. This process happens for every triangle in the scene, every frame. And usually a 3D graphics engine runs at 60 frames per second, and there could be upwards of tens of thousands of triangles in every scene. And that just goes to show how powerful our modern hardware is. But there is still one issue we did not solve. What do we do with depth? Because the way I showed you right now, if there were 2 triangles overlapping each other, the pixels in the middle would pass the edge function for both triangles. So what color do we represent? Now the simple answer is, well, the one that's in the front, right? But a computer does not innately know this. We know this as humans because we have a perspective on everything. But what we told the computer to do is basically entirely on a 2D surface. So it doesn't know what triangle comes first and which one comes after. So that case has to be specifically programmed into every graphics engine. And the solution is kind of easy. Basically what you would do if you detected that 2 pixels would pass the edge function is you make another vector between where the user sees the near clipping plane, and on the near clipping plane it would be precisely where that pixel is. Now that vector would continue, it would extend where it would come into contact to either one of the 2 triangles. Now every time it makes contact with a triangle, it's going to calculate the distance between the user and the triangle. And then the triangle with the smallest distance wins, basically. So it's going to be that color that's going to be represented on screen. Now this is a really simple execution of the depth buffer, which is what it's called, but it's just to show that there are a lot of problems that many people don't even think about when rendering a 3D environment, since how a computer sees a 3D environment is very unintuitive to a human mind. And it's only after we apply the depth buffer that we can see these 2 triangles living in harmony, where they both have their respective places on the screen. And that's how rasterization is done.